To take advantage of modern multi-core architecture, I spread work over as many cores as possible with Parallel 4. Previously, I was using Intel's Thread Building Blocks version 4 update 4 of the Parallel 4, which was fine. It was a static lib implementation, which is what I wanted, and it worked fine. Moving on to the newer versions of C++ 2023, it didn't compile with Intel Thread Building Blocks, the version I was using. So I had a look at Intel's new offering, the One Thread Building Blocks, that wasn't available in a static lib form. You could, I suppose, get the source from GitHub and compile it into a static library, but in their documentation it says it's a dynamic lib only, and I suppose there's good reasons for that. They probably know better than me why it shouldn't be built as a static lib. So I thought I'd write my own. Here we've got an implementation of how I use. Here we've got an example of how I use my implementation. So create a pool, a thread pool, and have some work. In this case, it's 1,000,000. It's a vector container of 1,000,000 unsigned integers, and I want to give each one the value of its index. So I've written a little class. We use the brackets operator that will get passed a range, and you go through that range doing whatever it is you need to do. So we create the range. So we say, starting at item 0 for 1,000,000 items over, in the case of this laptop, 16 cores, create a range, so that's R, and then given the body of the work, this class op instance, together with the range, we can now call my implementation of Parallel 4. And then after that, I've just written a little lambda that checks each item has got the correct index, so everything worked okay. In the real implementation, in the real usage case for this, in my code, my Parallel 4 implementation outperformed Intel's, and also the concurrency namespaces Parallel 4 as well. That was from the Parallel Patterns library. So if we have a look, we've got a range which basically takes an amount of work, a number of cores, and it splits up the range over those cores into subranges, and then each one of those subranges is executed on a core. We have a thread, so it's basically just a pool of threads, and each thread is either idle or busy. So we've got the total number of cores available minus 1. That's the number of threads I create in the pool. So there's no problems with intentions scheduling, because the calling thread is going to need to do some work as well. In that way, it will avoid deadlocks and also support recursive Parallel 4 calls. So we have a thread and we have a pool, which in this case is a collection of 16 threads. Then we've got the implementation of Parallel 4. So all it does is says, while there are some idle cores, execution units, schedule some work to be done on those idle cores. If all the work has been scheduled and allocated, then nothing else to do. If though there's work pending, then we execute at least one of those chunks from the range, one of those sub-ranges. And then after that, we wait until all the work has been done and return from our parallel 4 call. Like I say, I've tested this out on my actual code, which is vector graphics and raster graphics scene authoring, and it outperformed thread building blocks and it outperformed the parallel patterns library for that particular case usage. This case usage is just a simple dialog wrapper, which has got one button on it, and when you press the when you press the parallel 4 button, you'll come in here, create a range, execute the op over the range, and then check the results.